we've got everything we need now to figure out what dx over dt is. So dv over dt, we can plug in negative 384. 3x squared is now 3 times 8 squared. And dx over dt, we don't know what that is, but that's all right, because that's what we're trying to figure out. This is 64 times 3, so 192. Okay. So dx over dt is going to be negative 384 divided by that 192. Negative 2.
There's even numbers.
How about that?
How about that?
Yeah, good point. Let's label that. This is, first of all, the variable we have found is dx over dt. So there darn well better be a per minute or a per second or a per hour or some per something in there, because it's a rate. Be very aware of the relationship between the variables and the labels that they have. It'll help you. It'll help you a lot in this section. If you don't know, it's like, is this 384 v or v dv over dt? Well, if it's got a per something in it, it's a derivative. If it doesn't have a per something, it's just regular old non-derivative variable. Does that make sense? A little, kind of, sort of, hopefully. In this case, we're trying to figure out the label based on the variable. This is per. What's that? Okay, and then x, I like the per minute. I like the per minute. Okay, now think about what's the label for x. What did x represent here?
It's just one side.
One side. So x by itself would just be plain old centimeters, because it's the length of one side. Since it's dx over dt, it's not only centimeters, it's centimeters per minute.
There we go.
And why is it negative? It's decreasing, which if your ice cube is melting, you would think you would get a negative change on the distance of one side, because it's, melting. Fair enough?
Yeah.
All right, on the back I stole one from your book. We'll get through as much of this. Maybe. Like, that'd be super helpful. So here's the side of the swimming pool. Obviously, the thing on your paper is going to be much better than what I'm going to be able to reproduce by hand. Oh my gosh. Oh my.
Maybe squint your eyes a little bit.
This is why I printed it out and put it on paper for you. This will suffice for what we needed to do. Thanks. You know what? The heck with it. I'm just going to go all one-dimensional on it. And leave it at that. There. Alright, so this is 1 meter high. This whole thing is 3 meters from top to bottom, right? So this is the side of the pool. This is just if you took what's drawn here and just looked at the profile of it.
Alright.
So now you're below the ground next to the pool staring at it. Wow, it's concrete. Okay. Swimming pool is, they give you the dimensions. Of course, it's not a prism, it changes heights. Water's being pumped into the pool at 1/4 of a cubic meter per minute. Well, let's stop right there. 1/4 of a cubic meter per minute. It's a rate of change of what measure? of volume. The key here is cubic meter, that gives you volume, right? Per minute gives you rate. So what they are telling you is a rate of change of volume. Specifically, that rate of change is a fourth, right? There's 1 meter of water at the deep end. So we've got this going on. This is 1 meter high. What percent of the pool is filled? Well, this is not even calculus. But don't worry, we'll make up for it in part B.
Oh, good.
What percent of the pool is filled? How do you get the percentage of something?
Part over whole.
Yeah, the part that's filled up divided by the whole part. So we're going to have to figure out some volumes here, right?
Yeah.
Let's do volume of the whole pool. I think that's actually going to be easier. Maybe. I don't know. It's sometimes a little difficult getting the volume of something that's a weird shape. There's no formula in the back of your book for volume of a strange looking pool. You can look, I've looked. People have looked over the years, it never seems to show up. You're going to have to print it or what?
It's a misprint.
How many dimensions are there in volume? 3. How many dimensions are there in area? 2. So if I can take the area of this face, that gives me 2 of my dimensions. What is the third dimension that is not accounted for yet?
Like backwards.
How far it goes into Martinson's room, right? That's your third dimension. You can figure out how deep it goes. Take the area of the face and multiply it by that third dimension that's I haven't drawn here because I tried and it didn't work out well. Let's be honest. Do they tell you that that third dimension is? It's 6. It's not even a variable. It's just plain old 6. I like that. So all we really have to do is figure out the area of this weird shape, which really isn't that bad. Especially if you break it into separate shapes. This area of the face, we've got a rectangle up top. It's what by what? Okay, it's 12 across, so it's like 12 by 1. Yeah, 12 across, 1 high. That'll give you part of the area of the face. But let's add on the area of the triangle below it. So that's the area of the triangle is 1/2 base height. Yeah, base is still 12. That's the distance in 1 dimension. Height is 2. Yeah, because if the top part is 1 and the whole part is 3, that means this much is 2. And then times 6. Really, I should, be careful. 6 gets multiplied by the whole thing, not just that second term. This is not that tough. 12 plus, I'm going to say this is screwed up. What's that? Yeah, 12 and 12 is 24 times 6 would be 144. I guess I could look at my paper neck like I do all of them. Okay, so the volume here for the whole thing is 144. That's like an empty pool, or I guess a full pool, would hold 144 cubic meters of water. Now let's do the volume of the water. This really should be easier in a way, because the water isn't up to that funky part of the shape yet. So the water is really just a triangle, so the area of the face should just be a triangle. Times 6 again, the dimension. So it's the area of the triangular face, and then times 6. This is where it gets a little bit trickier, maybe. Area of a triangle is 1/2 times base times height. And then multiply that by 6. Now we know the height. Height's 1, right? What we don't know is the base. We don't know the horizontal distance. What? How'd you get that?
Like proportions.
Oh. It's something like that. Yeah,
Yeah, 'cause it's
you're on the right track for sure.
of its
All right. There's certainly a proportion to be made here. Check this out. Just drawing this lower triangle.
Oh yeah, shoot.
Let's pretend for a second that triangle were completely filled up with water. How far across would it be?
12.
12. How high up would it be? Well, careful. Whole thing's 3. The triangle part's just 2. So that means for every 2 units, because the water's going to fill up and it's going to hold that proportion, right? If this is 2, this is 12. But if you're only halfway filled up, this is half as much as well. It's not like you're going to, it's not like the water's going to stick to this side. It's going to fill up from the bottom.
It is 6, that was wrong.
So when they're full, the height is 2 and the base is 12. But when the height is only 1, which is the situation we got going on, when the height is 1, the base is 6.
Because it's half of the height.
Exactly.
Okay.
Or it's a 1/6 of. The height is always a 1/6 of the base. Man, I know. Yeah. All right. So we said when the height is 1, the base is 6.
18.
Grind it all out and you get 18. So when it asks you what percentage of the pool is filled with water, you do what divided by what?
18.
Yeah, there's 18 units of water for 144 total units. So you have I don't know, 18 out of 144 is 1/8, so 12.5% then, right? Not too terribly terrible. It's just a little geometry. Let's talk about part